Welcome back, everyone. In this video we're going to continue section 16.3. At the end of the last video we were given this vector field and we were able to show that it was conservative, meaning that this vector field is the gradient of some scalar function, of a potential function. Now we want to use the fundamental theorem of line integrals to evaluate a line integral of this vector field over a curve represented by e to the t sine t, e to the t cosine t, where t goes from 0 to pi. In order to do that, we need to know what the potential function of this vector field is. So just to remind you of how the fundamental theorem of line integrals works, f is conservative. We can find some scalar function lowercase f such that the gradient of lowercase f is equal to this vector field. And then if we want to evaluate this line integral, it's just the potential function at the end of the curve minus the potential function at the beginning of the curve. But the question is, how do we find f? And that's what we're going to spend most of our time in this video figuring out. There are two methods. And the first method is that we're going to take each of these component functions and integrate them with respect to a particular variable. So if this is a conservative vector field, that means the first component, p, is really the partial derivative of our potential function with respect to x. So if we integrate this partial derivative with respect to x, if we integrate with respect to x, we're undoing that partial derivative and we recover f. So f is really the integral of the partial derivative of f with respect to x, integrated with respect to x. We can do the same thing with the second component. The second component is a partial derivative of our potential function with respect to y. So if we integrate it with respect to y, we recover the potential function. So f, we can set this equal to the integral of p dx, which is also equal to the integral of q dy. So we're going to evaluate each of these integrals. How do we integrate with respect to a variable, a function that has multiple variables? Well, just like we did with partial derivatives, we're only going to concentrate on the x in this case and treat y as a constant. And for this integral, we're only going to concentrate on y, treat x like a constant. And so that's what I've written here. We integrate with respect to one variable, treat the other variable as a constant. And something else happens in this case. So these are indefinite integrals. I don't have any bounds of integration yet. And before, when you did an indefinite integral, you had to add an arbitrary constant. But here, I might also be missing some terms that only have y's in them. Because if I take a partial derivative with respect to x, a term that only has y, so let's say it's something like 5y to the fourth, that derivative is 0. There are no x's. So when I integrate, I have to take into account that I might be missing terms with only y's. When I take this integral, I have to take into account I might be missing terms with only x's, because a y partial derivative cancels out any terms that only has x's. And so when I integrate here, I integrate 2xy with respect to x. I get x squared y plus some function that I'm calling c1 that's only in terms of y. It might have terms with y's, it might have arbitrary constants, but there can't be any x's in here. And if you go backwards, if I take a partial derivative of this function with respect to x, this is going to completely go away because there are no x's in this function, only y's and constants. And if I take this partial derivative with respect to x, I get back to 2xy. For this other integral, I'm integrating with respect to y. So when I integrate x squared, treat that as a constant, so it gets a y, x squared y. And then minus y becomes minus 1/2 y squared. And then I have an arbitrary function of x, which could have terms with only x's or constants in it, for the exact same reason that I have a function here with only y's or constants. And these both have to equal f. So since these both have to equal f, I'm going to set them equal to each other and try to figure out what these arbitrary functions have to be. So if I set these equal to each other, I can see both sides have an x squared y. I can ignore that. This c1y function is equal to terms over here that only have y's, or arbitrary constants. So I have here this minus 1/2 y squared. That's part of c1y, and that's the only one. There can't be any y's in here. This is a function only of x. So there, I'm going to take an arbitrary constant and add it there. We're going to say this arbitrary constant is part of both of these functions. If I look at c2x over here, there are no terms that only have x's in them, right? This has an x squared y, which is present on both sides. This function only has y's and arbitrary constants, so it doesn't have any x's. So c2x is just an arbitrary constant. Now I want to write what f is. So I combine all the terms. F definitely has an x squared y in it, because I have x squared y on both sides. And now I look at all the terms here and I'm combine them to put them in f. If I have things that repeat, like this arbitrary constant, I only have to write it once. So f is equal to x squared y minus 1/2 y squared plus k. And k is an arbitrary constant. I can check my work by taking a gradient. If I take the partial derivative of f with respect to x, I'm going to get 2xy. This term cancels out, that term cancels out. If I take the partial derivative with respect to y, I get x squared minus y. And this is exactly equal to the vector field we started with. If I look back up here, capital F was 2xy, x squared minus y. So I found the potential function. This is the function whose gradient is given by this vector field. Okay, so that's one method to find your potential function. I'm going to go through a second method. And so here's the information we had before. It's the same vector field, 2xy, x squared minus y. Here's the curve that we want to integrate over eventually. We'll get there. But let's just go through a second method of finding our potential function. Now, in this method, we're not going to start by integrating both of these components like we did in the last method. Just pick one of them. Say, okay, I either pick this component or I pick this component. The way I'm doing this, I'm just going to start with the first component, 2xy. I know that these are partial derivatives of my potential function. So just like in method 1, if I want to recover my potential function, I need to integrate p with respect to x or q with respect to y. Just do one of these. So I'm going to integrate p with respect to x. We did this before. It's x squared y plus I might be missing a function that only contains y's and arbitrary constants. Again, because this is a partial derivative with respect to x, so if you take a partial derivative with respect to x, it cancels out terms that only have y's, or terms that don't have any x's involved. So that's what I might be missing. Now, I've integrated my first component with respect to x. The next step is to take the partial derivative of what you just found with respect to the other variable. Right? So if I integrated with respect to x, I'm going to take a partial derivative with respect to y of what I just found. And then I'm going to take this, after I've taken a partial derivative, and set it equal to the component that I didn't integrate. So this is going to get confusing, but just bear with me for a second. We have two pieces of information. We need to use both of these pieces of information to recover our potential function, to recover lowercase f. So far, I've just used p. Now I need to use this q somehow. So what I do, just to reiterate, I've taken p, I integrated it, that gives me f. But I might be missing terms with y's. So to figure out what those terms are, I take a partial derivative with respect to y, and say, wait a minute, this partial derivative with respect to y is exactly the second component of my gradient field, or my vector field. So this partial derivative, if I take this partial derivative with respect to y, that has to equal q. That has to equal the second component, x squared minus y. So that's why we do this. So I have my potential function f, x squared plus c1y, this arbitrary function that only contains y's and constants. I take a partial derivative of my potential function with respect to y, and I'm going to get x squared plus c1 prime of y. Now since this function is a function of one variable, when I take a partial derivative with respect to y, I just get an ordinary derivative. It's a function of one variable, I take a derivative, I can call this c1 prime. This partial derivative has to equal the second component of my vector field, which was x squared minus y. This is my q. Okay, so now I've set these equal to each other. I want to solve for this c1 function. I want to know what this, I want to recover this C1 function. So I'm going to solve this equation for C1, and so at some point I'm going to have to integrate, because right now what I have is C1 prime. So x squared plus C1 prime equals x squared minus y. I can get rid of the x squareds. C1 prime equals negative y. So now I know what C1 prime is. If I want to recover C1, I integrate, and I'm going to integrate with respect to y because this is a function of y. So I integrate negative y dy, and I get negative 1/2 y squared plus an arbitrary constant. This is just a good old integral. When you first learn how to integrate, we have to add our arbitrary constant. Now I just put everything together. I have what f was up here. This was my potential function, x squared y plus c1y. Well, now I know exactly what c1y is. So when I put everything together, I get that my potential function is x squared y minus 1/2 y squared plus an arbitrary constant. And this is exactly what we got when we did method 1. Before we go on, let me pause here and say that when you're recovering these potential functions, there's a lot involved. I personally prefer method 2. I think it's a little more straightforward. There's a procedure that you go through to find your potential function. Is up to you whichever method you want to use, as long as you get the correct answer. But what's important is that not only you're doing these things correctly, you understand why you're doing them. If you don't understand why this works, you're not going to know when to take a derivative, you're not going to know when to integrate, and most likely you're going to make a mistake somewhere. So it's vitally important not only that you integrate and take derivatives with the correct variable. Here I'm integrating with respect to x, here I take a partial derivative with respect to y, but it's important to understand why you're doing this so you don't make a mistake. This makes sense, integrating with respect to x, because this is a partial derivative of f with respect to x. It's coming from a gradient. Here I take a partial derivative with respect to y because I haven't used this component yet, and this is the partial derivative of f with respect to y, so I can set these equal to each other. It's vitally important to understand that to be successful with these problems. And once we do examples of three-dimensional vector fields, there's going to be even more of this. So when you're working on these problems on your own, make sure you have your notes handy so you can refer to them, and make sure you understand what you're doing each step of the way and why you're doing it. Alright, that being said, we've recovered our potential function. Now, at long last, we want to integrate it over this curve that was e to the t sine t, e to the t cosine t. So if I integrate this vector field, I can use the fundamental theorem of line integrals. Just plug the endpoints of the curve into my potential function. That was the whole purpose we went and found this potential function, so we didn't have to compute a line integral like we did in the last section. So now I need to find the endpoints of my curve. On this curve, e to the t sine t, e to the t cosine t, t went from 0 to pi. So that means r of b is r of pi. I plug pi into this curve. I get e to the pi sine pi, e to the pi cosine pi. Sine of pi is 0, cosine of pi is negative 1, so this becomes 0, negative e to the pi. Our starting point of this curve was 0, so r of a is r of 0. I plug 0 in for t. I get e to the 0 sine 0, e to the 0 cosine 0, sine of 0 is 0, e to the 0 is 1, cosine of 0 is 1, so this is just 0, 1. Okay. Now, at long last, I evaluate my integral. The integral of f, which was the vector field 2xy, x squared minus y, over this curve is the potential function evaluated at 0, negative e to the pi, minus the potential function evaluated at the point 0, 1. This is what the fundamental theorem of line integrals tell us. So now I just need to plug these points into the potential function that I found. So when I plug in 0, negative e to the pi, I get 0 squared times negative e to the pi minus 1/2 negative e to the pi squared, minus, I plug in 0, 1, 0 squared times 1, minus 1/2 times 1 squared. I don't have to include this arbitrary constant. For the same reason I don't include arbitrary constants when I do definite integrals. You could put it here, you could put a plus k here, but you're just going to put a minus k here. It's going to cancel out. It doesn't matter what that arbitrary constant is. So let's just forget about it when we do these line integrals. And I get an answer, -1/2 e to the 2 pi plus 1/2. And that's the answer, that's the integral, after all this work. So let's end the video here with this example. In the next video, we'll do another example of computing potential functions and calculating line integrals using the fundamental theorem of line integrals, and we'll explore some additional concepts.